But let's get started because I've dilly-dallied for like 4 minutes now. Let's get started on everything. Cool. So hopefully you guys all have the recitation handout pulled up. And before we dive into this material, there are a couple definitions and things that I think would be useful to review because they're going to show up a lot later. So the first thing is like, let's recall the following definitions, right? So the first thing is that we have like this group Z star n, and this is like the multiplicative group of mod n. It's all the numbers from 1 to n that are relatively prime to n, right? All the numbers from, or I guess 0 to n minus 1 that are relatively prime to n, that is the same thing. And specifically, this multiplicative group has that Z star n is equal to phi of n, where phi is the Euler-Toshin function. It's defined to be the number of numbers between 1 and n that are relatively prime to n, coprime to n, right? So the order of the multiplicative group Z star n is phi of n exactly. Cool. So this phi here, this is called the Euler-Toshin function. And phi is the Greek symbol behind it that we usually like canonically use to denote like this concept. And then there's some important properties about phi. And here, this function phi is actually multiplicative. It's kind of a multiplicative function. So I'll explain what I mean by that in a second. But what I mean by like kind of multiplicative is that if you have like phi of a, if you have like two numbers a and b that are coprime, then this implies that phi of ab is equal to phi of a times phi of b, right? So that means that if I had a number like n is equal to p1 to the l1, p2 to the l2, dot, 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 pk to the lk, then that would imply that phi of n is equal to phi of p1 to the l1 times phi of p2 to the l2, dot, 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 times phi of pk to the lk. Cool. So maybe it would be kind of cool to know like what phi of some prime to some power was, right? So let me tell you what that is. Phi of p to some power a is equal to p to the a minus p to the a minus 1, right? So what is like phi of 7? This is like 7 to the 1 minus 7 to the 0, which is equal to 6, right? What is phi of 49? This is equal to 7 squared minus 7 to the 1, which is equal to 42. Cool. So this is like the Euler function phi, right? Now specifically for 251, there are two things that are very important to know about this phi function, right? The two things that you need to know is that phi of p for any prime is equal to p minus 1, right? Because if you think about it, how many numbers between 1 and p are coprime to p? It's every single number 1, 2, 3, 4, all the way to p minus 1. They're all coprime to p, right? Cool. And then the other thing you need to know is that if you have two distinct primes, p and q, distinct primes, right? If you have two distinct primes, p and q, then phi of pq is the same thing as phi of p times phi of q, which is equal to p minus 1, q minus 1. These are the two most important facts that you need to know about the Toshin function for 251 cryptography. And we'll see why it's important later. Cool. Now there's a couple other interesting things, right? So one concept that you might have seen before is something called fast modular exponentiation. And it's basically this, right? Let's say I wanted to compute like the number like 7 to the, I don't know, 1024 mod like, I don't know, something 15, right? Let's say I wanted to compute this number, right? So what seems like the basic algorithm to compute this number, right? I would do 7, then what is 7 mod 15? Okay, it's this. Okay, take that number, multiply it by 7. What's that mod 15? Okay, it's this. Take that number, multiply it by 7 again. What's that mod 15? And I could do that 1024 times, right? But maybe that's not the best way to actually compute 7 to the 1024 mod 10, right? Instead, I could compute 7, and then I'm just going to drop the mod 15s, and then I could compute 7 squared, 7 to the 4th, 7 to the 8th, dot, 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 and then eventually get 7 to the 1024, right? Because I can just get to the next one by squaring. So this is kind of like the main idea. Instead of doing like 1024 multiplication operations, I can do log of 1024 multiplication operations. And that's kind of nice, right? So specifically, if I wanted to compute like some like base to some exponent, right? Like mod some n, what I could do is I could write out the exponent in binary, right? So like example, the exponent like, I don't know, 13 in binary tells me that 13 is equal to 8 plus 4 plus like 1, right? And then I could just compute b to the 1, b squared, b to the 4th, and b to the 8th, right? And then multiply these guys together, mod n. Cool. So that's basically the idea behind fast modular exponentiation. Cool. There's just a couple more things that I want to go over definition-wise before we jump into the material. The next thing is this idea of like the exponent universe, right? So if I want to compute something like, what is like 5 to the 2021 mod 10, let's say, right? Then this seems like it's pretty difficult to compute, right? Maybe I should have picked something not 5. Let's pick like 7. All right. Let's say I want to compute 7 to the 2021 mod 10. Okay, now this seems like it's pretty difficult to compute, right? But if I notice the following fact, that 7 is an element of z star 10, right? And the order of z star 10 is equal to phi of 10, which is equal to phi of 2 times phi of 5, which equals to 1 times 4, right? Then what do I know? I know that 7 to the 4th is congruent to 1 mod 10, right? So that should tell me that any like exponent can really be reduced mod 4, right? So specifically, if I'm doing something like a to the e mod n, then this is going to be congruent to a to the e mod phi of n mod n, right? I can always think about my exponents as living in the phi of n universe. And then the kind of like assumption here is that a is an element of z star n, right? So if like a and cap n are co-prime, then I can always think about a to the e, like raising a to some exponent, as really raising that exponent in the modular universe phi of n, because once I get to phi of n, things start wrapping around again, right? A to the 1 is the same thing as a to the phi of n plus 1. A to the 2 is the same thing as a to the phi of n plus 2. So whenever I'm dealing with exponents inside like a group, right, I can think about that exponent as really being reduced in the phi of n universe. Cool. So the key takeaway is that exponents live in phi of n universe. Cool. All right, and now there's one more thing that I want to talk about. And that last thing is like finding multiplicative inverses. Okay. And now if you're told that like a is in z star n, right? This is equivalent to the statement that the GCD of a and n is equal to 1. In other words, a and n are co-prime. Oh, I think I have a chat. What if the base is not relatively prime to the mod? So if the a and n here are not relatively prime, then I can't really say anything. But for cryptography, we will always be dealing with cases where the base is relatively prime to the mod. Because then I don't have any of my group theoretic results, which I'm really kind of drawing on right now, if that makes sense. Cool. Yeah. Okay. So finding multiplicative inverses, if I have a is like an element of z star n, that means that that's the same statement as GCD of a and n is equal to 1. Cool. And what is like, okay, let's kind of recall some fact from concepts. Maybe this is a little bit of overkill, but I just really want to drive home like how this like extended Euclidean algorithm really works and helps us find multiplicative inverses. So you might recall from concepts that there's this thing called Bézout's lemma, right? And specifically, I'm going to write it out mathy first, right? Let's say that I'm looking for the GCD of a and n. Like let's fix a and n to be 2 numbers. Okay, now if I think of all linear combinations of a and n that are positive, right, where k and l are integers, so all linear like combinations of a and n with integer coefficients that yield a positive result, right? If I think about the smallest element in this set, it gives me the GCD of A and N, right? So really what the extended Euclidean algorithm is doing, and maybe you don't really need to know it in this much detail, is it actually finds you the smallest linear combination with integer coefficients of the two things, A and N, right? Or whatever two things that you're running the extended Euclidean algorithm on. And the smallest element of the set is equal to the GCD, right? So specifically, after running the extended Euclidean algorithm on A and N, it'll spit out a K and L such that, and these will be in the integers, such that GCD of A and N is equal to K times A plus L times N. Cool. So now, if we run the extended Euclidean algorithm, right, on two numbers that are coprime, like if A and N happen to be coprime, that means that we're getting some linear combination that looks like this. Cool. So why is that cool, right? Because now if this equality holds, then this like congruence holds mod n as well. This implies that 1 is congruent to Ka plus Ln mod n, right? And just by laws of modular arithmetic, we can see that this is 0. So this means that K is equal to A inverse mod n. So this is kind of what the extended Euclidean algorithm is really doing behind the scenes in order to give you, right, multiplicative inverses. But again, the key takeaway here is that extended Euclidean algorithm can be used as a black box to compute inverses when they exist. Cool. Are there any questions on this material? I know that it's like kind of difficult to get your head around the first time. So I want to stop here and ask if anybody has any questions. Cool. All right, so let's kind of recap where we're at right now, right? We recalled the definition of Z star n, the multiplicative group. We talked about the Euler-Toshin function and how it tells you the number of integers in Zn that are relatively prime to n, and that's also the same as the order of Z star n, right? So by Lagrange's theorem, like a group element to the order of the group is always going to be equal to the identity. Therefore, we can think about our exponents as living in the phi of n universe always, right? We talked about fast modular exponentiation. Exponentiation is not an easy thing to do in general, right? But in some modular universe, exponentiation is actually a polytime thing because we can take advantage of nice properties of modular arithmetic. And we can compute multiplicative inverses in a modular universe by using the extended Euclidean algorithm, which is a polytime algorithm, right? So we've just kind of discussed like some definitions and some like kind of black boxes that run in polytime that'll be useful for us to do cryptography with. So if there's no questions here, I'll continue with the recitation material. Cool. All right, so let's start with question 2. And we're going to discuss a protocol called Diffie-Hellman. So what is Diffie-Hellman? Diffie-Hellman is kind of a way for two parties, in this case, Apoorva and Bhagwat, to communicate over an insecure channel, right? Communicate publicly over an insecure channel and agree on some secret key, right? So I could be talking to Bob, and Bob and I can be having our conversation out loud, and anybody can listen to what Bob and I say, right? But at the end of the conversation, only me and only Bob will know our secret key. Nobody else will know our secret key, which is a kind of cool result, because once Bob and I have agreed on a secret key, we can use that secret key to kind of communicate with each other like messages, right? So we both agree on some secret key. Now we can use maybe like one-time pad or something to communicate with each other over the internet in a secure way. Cool. So that's the idea of Diffie-Hellman, and that's why it's cool. So let's talk about this protocol. Right, so we have Apoorva and we have Bhagwat. And so Apoorva will pick P, right? Which is a large prime, right? He'll pick a generator B and Z star P. Cool. He'll randomly draw E1 from Z phi of P, right? He'll compute B to the E1, right? And as I'm writing all of this, you should be thinking about every single step and whether it's something that can be carried out in poly time, right? And then he'll send P B, and B to the E1 to Bugbutt. And notice that this stuff that he sent can be seen by anybody, right? Then Bugbutt is going to, he is going to randomly draw his own exponent E2, again from Z phi of P. Why phi of P? Because the exponents live in the phi universe, right? And he will compute B to the E2 in Z star P, right? And he'll send back B to the E2, right? So now some adversary can see everything that's on these arrows that I've drawn, right? They can see P, B to the E1, and B to the E2. Cool. And now they can both compute B to the E1, E2, which is their shared secret key, by taking their E1. So like Apurva knows E1 and he knows B to the E2. So he can do B to the E2 to the E1. And similarly, Bugbutt knows B to the E1 and knows E2. So he can take B to the E1, E2 mod P. Cool. So the first question, and how is the generator found? Wow, you just asked like the most challenging question for 251. Okay, but there is no efficient algorithm to find a generator. I'll get into this after we go through this question. Yeah, I'll get into that in a second. But first, let's just assume that you can pick a generator in Z star P. Cool. Good question. Very good question, Brandon. Okay. So what we're going to do is we're going to look at this algorithm and talk about why every step needs to be the way that it is. So in step 2, why did we pick B as a generator? Since like this weekly review is kind of small, we can make this more or less kind of like a recitation with participation if you guys would like to participate. If you don't, that's cool. I will just answer all the questions, but I want to give you guys the option to. So I'll ask the floor. Why do you guys think that in step 2 we're picking a generator? Does anyone have an idea? I'm gonna do the Ryan O'Donnell thing where I like do something really meta and talk to the people who are watching this on video later. If you're watching this video, feel free to pause now and think about why B should be a generator. Okay. Doesn't it have to do with the discrete log problem? Somewhat. But yeah, this is here, Brandon said something. It can generate all elements of the field, so your search for the space of the exponent is as big as possible. Yes, exactly. So the reason for that is because the whole idea is that if somebody wanted to break this protocol, yeah, Kunal and Brandon, like a combination of your answers is completely correct, right? The reason is that if B is not a generator, right, then really to break the protocol, right, an eavesdropper wouldn't really need to know like B to the E1, right? Eve doesn't need B to the E1. Actually, Eve needs some like E prime such that B to the E1 is congruent to B to the E prime, right? So okay, there's kind of like a billion ways to explain this, and I don't know what's going to do it for you guys. So I'll try this verbal explanation first, right? We talked about if I'm working in the multiplicative group mod n, right? That means that I can consider all of my exponents as living in the phi of n universe, right? And the reason I say that is because all elements in the mod n universe, when raised to phi of n, equals 1, right? So once you get to phi of n for any of those elements, it starts to wrap around exponents wise, right? But if you have an element that's not a generator, that means that the order of that element, or the smallest positive exponent that you can raise that element and get the identity, right, is less than phi of n, which means that even before you get to phi of n, like powers of that element have started to wrap around already, right? So now you're not guessing, now you're not making like an eavesdropper guess exponents from the range 1 to phi of n. You might be making the eavesdropper guess exponents from a smaller range, right? Specifically 1 to the order of any element that you've chosen, right? So wouldn't it be best to choose an element whose order is the same as the order of the group, if possible? Like choose an element with the highest order, or a generator, right? That way you're making the life of someone who's trying to hack you as difficult as possible. Does that make sense? Or would somebody like me to elaborate on that more? Okay, I'll continue then. Cool. So in lines 3 and 5, why are the random exponents chosen from the set z phi of p? Right. So we talked about that. It's because, right, the exponents can be chosen in the in the phi of n modular universe, right? Since we're working in mod p, right, the exponents live in mod phi of p. In fact, like I said, the exponents live in mod phi of the order of the b that you picked. But since b is a generator, right, the order of b is the same as the order of c star p, which is phi of p. If that didn't make much sense, then ignore that. But yeah, just remember the exponents will always necessarily live in the phi of p universe, sometimes a smaller universe for certain elements. But assuming the phi of p universe is always safe. Cool. Lines 4, 6, and 9 involve modular exponentiation. We talked about at the beginning how you can do fast modular exponentiation. And an eavesdropper can recover, can see b to the e1, and b to the e2, and p, right? Can they recover b to the e1, e2? And the idea is that there's no known efficient algorithm for finding, like, given b and b to the e, right, mod p, there's no known algorithm to uncover e, right? This is called a discrete log problem. Cool. And why is this protocol useful, right? Now that you have a secret key that you guys have agreed on, you guys can use it to, I don't know, communicate however you want with some, like, I don't know, fast private key encryption scheme, like one-time pad. Cool. All right. So getting back to Brandon's earlier question, was it Brandon? Yeah, Brandon's earlier question about how a generator is found. So picking a generator B and Z star P. So this is very outside of the scope of 251, but I'll maybe say a little bit of a few words about it. Z star P, remember that, okay, you might not, this isn't something we covered, but Z star P is a multiplicative group, right, mod P, which necessarily will have a generator. And then once you have a generator, that means that you have, like, kind of, like, if there is one generator at least, then you know that there's, like, a certain number of generators specifically, right? Because if G is a generator, I won't go into this too much, but, like, once you know that a generator exists, and there will be a generator in Z star P always, once you know that a generator exists, a lot of generators exist. So what you can do is you can kind of, like, randomly pick numbers and then check to see if they're generators by making sure that, like, their order is exactly the same as the group's order. And then hopefully you find one quickly. Unfortunately, there's no known algorithm for checking if something is a generator efficiently, unless you happen to know the prime factorization of p minus 1. And the way this is done in practice is that usually you pick a prime, not completely randomly. It says pick large prime, right? It's like you're not going to be, like, just generating a random prime. You're just going to kind of go to the internet or something and pick, like, oh, that's a big prime. I'll use that. Oh, that big prime's p minus 1 happens to have, like, this prime factorization. And then once you do that, then there is an algorithm for finding a generator efficiently. But it's extremely outside of the scope of 251. If you want to talk about it later, I'd be happy to. Cool. Let's talk about El Gamal if there are no questions on this. Oh, my grandpa is calling me, but I will call him back after this. Cool. So let's talk about El Gamal, right? So El Gamal can be thought of as kind of like doing Diffie-Hellman, but then once you agree on, like, a secret key, you encode a message with it. I thought the exponent has to be chosen mod phi of n, where n is the mod, not the base. Yes, so the exponent is chosen mod phi of p. The mod here, we were working in the mod p universe. Sorry, Bharat, I don't fully understand your question. Can you elaborate a little bit? Feel free to unmute yourself if you're, like, not in a super.
I think you said that earlier when you were explaining why the random exponents were chosen from the set z phi of p. You were saying because b's order is the same as p, but doesn't the order of the base not matter?
Okay, the reason I was saying the order of the base, right, is because once you get to, like, if you think about the numbers b to the 1, b to the 2, all the way to b to the order of b, right? Those are all of the numbers in z star p that b can generate, right? Because once you get past b to the order of b, then you start to wrap around again, right? So I was saying that really, like, if you have a fixed base, right? If you have a fixed base, you can think about the exponents as living in the order of that fixed base, right? Now we know that the order will always divide phi of p, right? So for a general base, we know that it's always okay to assume that the exponents live in the phi of p universe. But for a fixed base, you can say something even stronger, that the exponents live in the like the order of that fixed base's universe.
Got it.
Does that make sense?
Yeah.
Cool. Yeah. All right. So let's talk about El-Gamal, right? So this can be thought of in two ways, right? So like one way that I think about El-Gamal is like basically you're doing Diffie-Hellman. We agree on some secret key, which happens to be like b to the e1, e2, right? And now if I want to send you a message, I'll just send you like my message times our secret key, right? And then if you want to kind of like decrypt my message, you'll just take message times secret key and times inverse of our secret key, right? Because secret key is just like some number, and then you'll be able to find like the multiplicative inverse of that number easily using extended Euclidean algorithm, right? So you'll just be able to decrypt like that, right? So that's one way of thinking about El-Gamal, right? That two people talk, they agree on a secret key, and then they use that secret key, multiply it with a message, and then they can decrypt that message by multiplying it back with the inverse of the secret key. There's another way to think about El-Gamal, and it's actually as a public key encryption scheme. So for this question, I propose that instead of thinking about the two parties as Apurva and Bhagwat, we think about the two parties as Bhagwat and anybody else, right? So the idea here is that anybody can talk to Bhagwat. Cool. So Bhagwat will basically start this scheme off by picking a large prime P, picking a generator in Z star P, and then randomly picking E1 in Z phi of P, right? And recall that, yeah, phi of P is the order of B since B is a generator. And then compute B to the E1 mod P, and then send out P, B, B to the E1. And now when I say this sending out, really what I'm saying is that like Bhagwat has like a public website that anybody can kind of come and visit, right? And on that website, he has posted like a secret key, a public key saying, hey, if anybody wants to communicate with me, you can communicate with me by using these three parameters. All your messages must be encoded in the mod P universe, right? Here's the base that I'm using B, and here's like the base to some power. You don't know what it is, but kind of use this information to send me a message in a way that only I'll be able to read the message. So, right, you can think about Bhagwat as having kind of like a blog, him posting at the top of the blog, P, B, B to the E1, and then a bunch of people posting a bunch of like ciphertext messages underneath his blog, but nobody can kind of read each other's ciphertext messages and decrypt what they're saying except for Bhagwat. Right, Bhagwat can kind of scroll through his blog and be like, this person's telling me this person's telling me that. Okay, cool. Right. So that's kind of how that works, right? And now if anybody wants to communicate with Bhagwat, right, they have P, B, B to the E1. They can randomly choose some exponent E2 in Z phi of P, right? And they can compute B to the E1, E2 as B to the E1 to the power of E2, right? And they can also compute B to the E2, I suppose, right? These are just using fast modular exponentiation, right? And then can multiply M by B to the E1, E2 and send back to Bhagwat B to the E2 and M B to the E1, E2, right? So in case you haven't noticed here, like one of these major themes, right, is that like, how can I explain it? Like Bhagwat has like a special kind of key, two special kinds, like two identical keys, right? And then he has a box. He puts one of his keys into a box and sends it to anybody, or let's call it Apurva in this case. He puts one of his keys into a box and he sends it to Apurva. Now Apurva also has two like identical keys, right? Apurva puts one of those keys into a box and then sends it back to Bhagwat, right? Now both of them know how to take like a box with the other person's key and put their own key in, right? And so they can both end up with a box that has like one copy of Apurva's key and one copy of like Bhagwat's key. right? This idea is like called a one-way function, and it's defined in the notes. The idea is that it's kind of like easy to put in, but hard to take out of the box, right? So they're both kind of putting one thing into the box and sending it to each other in a way such that they both can like end up with a box with two things in it. But any kind of person who's observing, right, they never get to see like any of the keys. They only see like partially completed boxes. They'll never see a completely completed box. All right, maybe that analogy doesn't make much sense. I'm getting ahead of myself. There's kind of like a billion ways to explain this. So if anything is like really confusing, please feel free to stop me. Cool. So yeah, so like I was saying, Bhagavad can send this to everybody, right? And then anybody who wants to respond to Bhagavad and communicate with him can send back this, right? And now Bhagavad will also be able to compute b to the e1, e2, right? Since he has e1 and he's been given b to the e2, b to the e2, e1, right? And then he can compute, let's just call this s. He can compute s inverse, right? And then ms s inverse is going to be equal to m. Cool. So that's the idea here, right? Essentially, all that happened is it was Elgamal to, it was Diffie-Hellman to establish a secret key, and then like Apurva sends Bhagavath m times s, and then Bhagavath just takes ms s inverse to get back m. Cool. So let's go through the questions together. So p is equal to 17, b is equal to 3, right? So let me just start it off like this. Bhagavath, right, has posted this public key. Specifically, p equals 17, b equals 3, and b to the e1 is equal to 6. Now, privately, Bhagavath knows this, that e1 is really equal to 15, right? Now, Bhagavath receives from somebody who wants to communicate with him, right, an incoming message, incoming encrypted message, where he's told that b to the e2 is equal to 7, and that m to the times b to the e1, e2 is equal to 1, right? So now the question is, how can Bhagavath decrypt this message? So I'll give you guys like a second to think about it. If anybody has any suggestions, please let me know. I can also go through the math if you guys are feeling lazy. Yeah, raise to the power of e1, then find the inverse. Perfect. So to decrypt, right, what Bhagavath can do is he can take b to the e2 to the e1, right, which is equal to b to the e1, e2 mod p. Cool. So basically, Bhagavath needs to figure out what 7 to the 15 is congruent to mod 17, right? So how can we figure this out? Well, notice that 15 is equal to 1 plus 2 plus 4 plus 8. So really, 7 to the 15 is equal to 7 to the 1, 7 to 7 to the 4th, 7 to the 8th, right? So let's figure out what each of these things are by fast modular exponentiation, right? So 7 mod 17, right? Then we have 49 mod 17, which is negative 2, since 51 is a multiple of 17, right? And then we get 4. And then 4 squared is 16, which is minus 1, right? So then we put this all together. And what does this give us? It gives us 8, 56. 56 mod 17, which is congruent to 5 mod 17, right? So we've computed that kind of like the secret that Apurva multiplied their message by was 5. So now we want to know what the secret inverse is, right? So 5 inverse is congruent to 7 mod 17, right? Why? Because like 5 times 7 is equal to 35, which is 1 more than 34, right? So 5 times 7 is 1 mod 17. To do this, usually you don't eyeball it. It's easy to eyeball because the numbers are like small, or like not easy, but like doable to eyeball because the numbers are small right now. But in general, you probably want to use the extended Euclidean algorithm. I just don't think it'd be a great use of our time to go through the steps of that. Cool. You can look it up though if you're curious. All right, does anyone have any questions about like this problem? Or like how Elgamal works in general? Why it's useful? So yeah, so this was an example of a public key encryption scheme, which is really cool, right? Think about like one-time pad, Diffie-Hellman, and then using one-time pad, right? Like the problem with like private key encryption schemes is that you need to remember secret keys with so many different people, right? If I want to communicate with like 10 people, I need to remember like 10 different like secrets and things, and that's kind of annoying, right? If n people all wanted to communicate with each other, they'd have to remember like up to O of n squared keys. That's kind of annoying. Here, like this. Cool. Yeah, if like n people wanted to communicate with each other, all with like private keys, where everybody has like a pairwise key, that's like O of n squared keys. That kind of sucks, right? With public key encryption, somebody can just post something on the internet and be like, hey, if anybody wants to talk to me, you can talk to me like this, right? And nobody else will be able to read the messages except for me, which is kind of awesome, right? For two reasons. One, there's a lot fewer things to keep track of. And two, right, like anybody who wants to talk to you can do so without like a handshake prior, right? Like if a Nigerian prince wanted to contact you, then he's well within his right to like do so. It's kind of the idea. The drawback about public key like encryption schemes is that typically private private key or like symmetric key encryption schemes are like faster in practice. So yeah, so it is, even though they're both polytime, right? Like it's more efficient to communicate with each other via like one-time pad because it's much easier to take XOR than like do fast much of an exponentiation. Cool. All right. Am I good to scroll down? Okay, cool. All right. So now let's talk about the coolest thing ever, which is RSA. So this is like a very famous public key encryption scheme, right? That's still used on the internet today. Oh, the drawing on my screen is laggy. I tried to optimize. Is anybody else feeling that my drawing is kind of laggy? Oof. Okay, is there anything you think I can do to help that problem? I can stop sharing the reshare. Okay, I'll try that. Cool. Okay. Let's see how this works. Okay, cool. So let's talk about RSA. So specifically, there's going to be a receiver and there's going to be a sender. So the receiver will first publish like a public key, right? And then after the receiver has published a public key, anybody who ever wants to talk to that receiver can do so via their public key, right? So here's what the receiver will do. Choose two large primes, P and Q, that are distinct, right? And then compute n is equal to P times Q, and then they'll choose some E in Z star phi of n. Huh, that's weird. Usually like the exponent just comes from phi of n. Why are we choosing Z star phi of n? Something to think about. Cool. Now publish the public key n E, right? They will compute the decryption or private key D is equal to E inverse in Z star phi of n. Okay, maybe that's why E came from Z star phi of n. And upon receiving a ciphertext or an encrypted message, that ciphertext is just an encrypted message, upon receiving a ciphertext C, compute M is equal to C to the D, right? Because why? C is really equal to M to the E, right? Mod N, right? And then M to the E to the D is equivalent to M to the ED mod phi of n, which is equivalent to M to the 1 mod n. Okay, and now what the sender has to do is pretty simple. If they want to talk to the receiver, then all they have to do is, right, encode M in Z star n, and then the second thing is they have to send M to the E in Z star n. Cool. All right, awesome. So now I'm going to leave this here and we're going to go through kind of these problems together. So the first question is explicitly write down the values that the receiver knows and the values that the adversary knows, right? So the things that the receiver knows, right, is like N, P, Q, N, E, and D, right? This receiver knows P, Q, N, E, and D, right? Or just P, Q, and N, E, right? Like everything else can be computed from there. The receiver knows P, Q, N, and E, and the sender only knows like N and E. Right? So the P and Q are kind of like kept secret, right? Only the receiver knows P and Q. They don't publish P and Q. Cool. What is the advantage that the receiver has over the adversary that allows the receiver to recover the original message while the adversary cannot, right? So if an adversary was trying to like decrypt a ciphertext sent to the receiver, what advantage does the receiver have that the adversary doesn't, right? It has something to do with P and Q, but can someone tell me what exactly? Phi event. Stephen, can you elaborate a little bit? Or anybody. Doesn't necessarily have to be Stephen. But yeah, you're completely right. Why is it that the adversary? Cool, yeah. So since we know P and Q, we can easily calculate phi of n, which is P minus 1 times Q minus 1, right? And how are you going to figure out what D, like E inverse is in Z star phi of n if you don't even know what phi of n is as a number, right? So there's kind of an assumption here, right? And that leads really well into question 3. Suppose the factoring problem can be solved in polytime. Given some number, we can find polytime its factors. How can you break RSA? Well, I won't like ask you guys this because we just answered it. But the idea is that like if you could factor numbers, then you could factor cap n, right? And then P and Q would no longer really be secret if you could easily look at n and be like, oh, that's just like this prime times that prime, right? Cool. So yeah, so the reason, the kind of assumption here, one of the assumptions that makes this like protocol like legit is that it's hard to factor numbers in general. If it were easy to factor numbers, then anybody could compute P and Q. And then once they compute P and Q, they can compute phi of n. Once they compute phi of n, they can compute like the decryption private key D by using extended Euclidean algorithm. Cool. Question 4. Why must P and Q be distinct? Can somebody tell me what would go wrong if P and Q were not distinct primes? This is kind of a hard question, I would say. Yeah, if P is equal to Q, what would go wrong if n equals P squared, essentially? Yeah, yeah. So the idea is that you'd be able to take the square root of n kind of and find P, right? So maybe this is kind of like potentially less of a theory thing and more of like an in practice thing, right? But if somebody were trying to kind of hack you, right? What's the first thing they would do? Would they be like, haha, I'm going to be the first person ever to solve like the factoring problem. I'm going to find a polytime algorithm to factoring. No, if somebody wanted to hack you, the first thing they would do is to check if you were being stupid when you set up your public key, right? So they'd run a bunch of checks, such as, oh, there's no way they were dumb enough to make like P and Q the same prime, but just in case, let me check, right? Because I can check pretty quickly. It's not that big of a waste of time if I just check, right? It's like a hacker would check to make sure you didn't do anything dumb first, right? So yeah, there's no like easy way to obviously look at a number and be like, oh, that's obviously a square. But like you'd first do your due diligence and just make sure that like the person you're trying to hack didn't like mess up gravely. And if you did, then like, yeah, so someone would check to see basically, is this a square? And if it is a square, you can kind of figure out like by binary searching what P is. And if you figure out P, then you know what phi of n is, right? It's P squared minus P. Cool. Does that explanation make sense? Does anyone have any questions about that? Cool. So the next question is, why must the encryption key E be an element of Z star phi of n? And I kind of clued into this earlier, so I won't ask you guys. But it's because you want there to exist an inverse in the phi of n universe, right? We wanted m to the e, like we wanted this e here to have an inverse in the phi of n universe. Otherwise, we wouldn't be able to like exponentiate m to the e by something else to get m to the ed, such that ed is the same as 1 in the phi of n universe. You want e times d to be 1 phi of n universe. Cool. Now this last question is also like not super obvious, but what if m came from z mod n, but wasn't like in z star n? Like what if m was in zn, but not in z star n? What could go wrong in that case? Is this something to worry about? That means m is a multiple of things in z star n. Close. I think you have the right idea. I think your wording is just slightly off. I don't really follow what you mean by multiple of things in z star n. I think that's the right idea though, if I understand what you're trying to get at. So I mean, no, I don't think it's exactly as you phrased it. Like if you multiply elements in z star n, then you'll stay in z star n because of like closure of the group operation. But I think you're trying to get at that it's a multiple of something. Yes, yeah, okay. So yeah, so essentially if you have like an m in zn, but not in z star n, that means that you found something that's a number between 1 and n that isn't relatively prime to n, right? And if you're not relatively prime to the product p times q, right? That means that you either have p as a factor or q as a factor, right? So that means that you found some multiple of p or some multiple of q. And using the extended Euclidean algorithm or otherwise, you could pretty easily from that point onwards figure out, by easily I don't mean like an easy mathematically or conceptually, I just mean easily in terms of like how fast you could do it. You could pretty easily figure out what p or what q was. Once you figure out p or q, you're busted because n divided by p gives you q, n divided by q gives you p, right? So you basically factored n, right? So if this does happen, if the message that somebody tries to send you happens to be in zn set minus z star n, right, then they found a number that happens to be a multiple of p or a multiple of q. Fortunately, there aren't so many numbers in the range 1 to n. If you choose p and q to be really large, the probability of somebody accidentally trying to send you a message that is in this set, zn set minus z star n, is really low. So like, yeah, I guess the whole like MO of cryptography is that like nothing's really guaranteed. It's just with really high probability stuff works out. Does the adversary know m? So the assumption of this question is that like somebody was just trying to send you a message, right? And somebody basically found a number that isn't like relatively prime to cap n, right? And we're calling this number m, right? So if somebody like happens to stumble across a number m that is between 1 and n that's not co-prime to n, then somebody accidentally factored n. Does that make sense? Like it's always possible that if I give you a really large number and tell you like, oh, guess one of its factors, I bet you can't. There's a tiny probability that you like actually get it right. Does that make sense? Yeah, cool. All right, so does anyone have any questions about RSA? Okay, well, let's move on to the last part of the recitation. So it's question 5, and it's called L commit. So in this part, we're going to be talking about commitment schemes, right? So what a commitment scheme is let's say that I was talking to Ada and I said, hey, Ada, I bet I can tell you like how many like times you'll like, let's say before the semester, I'm talking to Ada and I say something like, hey, Ada, I bet I can predict the number of times you're going to say beats me on Diderot this semester. And you'll be like, there's no way you can predict the number of times I'm going to say beats me on Diderot. And I'll be like, yeah, watch me. But obviously, I can't tell a DA like you're going to say it 7 times because then he'll make sure to not say it 7 times. So maybe I want to like have a way that I can commit to a number and then prove to a DA once the semester is over, look, I really did guess that you were going to do it 7 times, right? So this is the kind of like scenario in which somebody would use a commitment scheme. I would give a DA a locked box that had the number 7 inside of it. And then once like a DA, once like the semester was over and I was ready to unlock the box, I would give a DA the key to unlock the box. He would unlock it and then be like, oh, the number 7 really was in there. I guess you really do know me well, Kabir. Okay, so yeah, that's the idea. Cool. So there are 2 kinds of things that a commitment scheme should do well. In order to be a good commitment scheme, it needs to have 2 properties that we care about, right? One property is called binding, which means that like once I've locked that box, when I unlock it, it better be like guaranteeably the same element that I put in there in the first place, right? Otherwise, this commitment scheme is stupid. If I like lock 7 in the box and then like give a DA like a special key such that when he opens the box now he sees like 9, right? Then this wasn't a very good commitment scheme protocol. There's no guarantee that like when he opens the box he sees the same number that I originally put in. The second thing is called hiding, right? When I give a DA the locked box, he should have no like idea what's actually in that box. Cool, until it's like unlocked, right? So we're going to talk about a specific commitment scheme called lcommit, which is very similar to lgamal, and we're going to talk about how it has the properties like binding and hiding. Cool. So here's the idea, right? Alice, oh, what happened to you? Oh, okay, what's going on with my pen? Okay. Maybe my pen ran out of battery. All right, I apologize, guys. I don't know why I'm having some technical difficulties. I'm actually not able to write right now. Can I use my finger? No, apparently not. Interesting. Okay, I guess I'll just talk this question out and you guys can read the recitation solutions to this. I'm really sorry about that, and I can answer any questions afterwards verbally. But yeah, we are like a little bit over time anyways, but I'll kind of talk this out, the idea. The idea is that Alice is trying to commit a value to Bob, right? And we're going with something called, we're going to assume something called the decisional Diffie-Hellman assumption, right? And specifically, actually, in hindsight, it is very difficult to talk this problem out. So maybe what I'll do is I'll post a recitation video later if anybody's interested. Let me know if there's interest in that. You guys can try reading the solutions, and if anybody would like, post on Ditero, and I will like kind of record myself explaining this question because I think there is like a lot to this question. I don't think it would be doing it justice if I just kind of talked it out loud. So if anybody has any like interest, please let me know, and I'll record like a video later today and post it on Ditero explaining like lcommit. Cool. I don't think it would be right to just talk this out because I think it is a little bit complicated. Okay, cool, yeah. So somebody said that video would be nice. So I'll definitely do that later today. I don't know why my pen ran out of battery, really sorry. I'm really new to like this iPad teaching, so apologize for that. Does anyone have any conceptual questions about anything crypto related?